Good morning. My name is Florentin Smarandache, professor of mathematics at the University of New Mexico, United States. And thank you very much for inviting me to have a presentation for this conference on artificial intelligence. The first part will be about my book called Extenics in Higher Dimensions that I wrote together with some friends when I was in 2012 an invited researcher at the Guangdong University of Technology in Guangzhou, China. So we we work together with many researchers, some of them from Romania, like Victor Vlădăreanu, Luigi Vlădăreanu, Mihai Liviu Smarandache, Tudor Poroiu, Stefan Vlăduțescu, and also with researchers from China. So I got familiar to the Extenics, which was set up and developed by Professor Kai Wen. And I extended the Extenics function and distance from one dimension to 2, 3, and n dimensions. And I did some applications. The book is available online. You can see its link fs.unm.edu/extenics _book.pdf. It's open source, so you can download all the time, anytime. Now about the presentation and the research I did several years ago. We talked about linear and nonlinear attraction principle in Extenics, and then the network of attraction curves. So in case of nonlinear attraction, we could use any kind of curves because that's how it is in our everyday life. So if we consider a point of attraction, other points outside may follow various curves, even linear directions to be attracted by that point. So if we consider an arbitrary set in a universe of discourse U of any dimension and an optimal point O, then the point of coordinates P, of coordinates x1, x2, xn, and so on from the universe of discourse is linearly or non-linearly attracted towards this optimal point. So this was the idea of Professor Kai Wen, which was extended to n dimensions. The point O is considered an ideal point, and it has a force of attraction. We could do an attraction through many curves or many linear lines, many linear attraction of the same point. Of course, we consider the smallest distance of attraction between a point and any point and the optimal point. There are many such examples. How can we attract? And then the main idea of Professor Kai Wen was to consider as negative distance a point which is inside of an object, for example, or a closed curve or closed object, and for the points which are on a frontier of the corp will be considered distance 0 to the corp, and the points which are outside will have a positive distance, and the distance is measured from the point, from the outside point to the optimal point or attraction point, following the attraction lines or in general attraction curves. So I have explained this one here. So if a point belongs to the interior of S, the corp S, then the distance is less than 0 if the point belongs to the frontier of the uh, set or corp S, the distance is 0, and if the point is outside, so outside of S, we have a positive distance. Now, the dependent function was defined in a following way along a curve and with respect to set S in a following way. We consider this is the distance K n, so dimension n of the point of coordinates x1, x2, xn is equal to the distance between the point and S2 over the distance, the difference of distances between the point x1, x2, xn of coordinates to S2 and then to S1. And in the same way, we have the properties here that if the point belongs to the interior of S1, then the distance it's bigger than 1. If the point belongs to the frontier of S1, then the distance is 1. If the frontier belongs to the interior between S2 and S1, the distance belongs to the interval 0, 1. If the point belongs to the interior of S2, it's 0, and if the point doesn't belong to the interior of S2, the point is less than 0. So this was the first step. The first step was actually to do the extension in two-dimensional space, and then we went to three-dimensional and n-dimensional. So we can see now if we have a point, let's consider O, the attraction point, and the point P inside of this rectangle. So we have a two-dimensional object. So the distance between P and this rectangle, it's P prime, and it's negative because P is inside of the object. So, and it's negative, and it's measured on the line that attracts P to O. So this is the line that attracts P to O, and then we extend it to intersect the object. So it will be P prime. So this will be the negative value of distance between P and P prime. Now, if we have a point which is on a frontier, for example, P prime, so a P second here, the distance is considered 0, and it's measured on the same direction, attraction to the point O. Now, if we have an object of bigger dimension here, okay, if we have a point which is outside, like this one, P is outside the object, we measure the distance between P and the rectangle, the object AMBN, but on a line that attracts P to O, so the distance will be positive and it's P prime. So this is a positive distance. Now for having if we consider therefore two rectangles, one, the smaller one included in the other one, and then considering that they have the same optimal point, O1, O2, that coincide. So we have here O, and this will be also the center of symmetry. Then for a point of coordinates x, y, any point on dimension 2, R2, one has that the distance between the point and the small rectangle here, it's bigger than the distance between the point and the bigger rectangle here. We have the formula, therefore dependent function now. The dependent function on two dimensions is rho between the point xy and m, AMBN, the bigger rectangle, over the difference of distances between the point x, y, point of coordinates xy, and the bigger rectangle minus the distance between the point x, y, and the smaller rectangle A0, M0, B0, and 0. Now, in general, if we have any closed curve, so not necessarily a perfect geometric figure like a rectangle, triangle, trapezoid, and so if we have here two finite closed curves, so this is a curve here, the smaller inside, and this is a bigger one outside. One, and if we consider an optimal point, not necessarily the symmetry center, and we assume the optimal points are the same for this nest of two surfaces. And we have, again, the attraction point. So O is the attraction point. In the same way, we compute the distances and dependent functions between a point P2, for example, and a smaller surface, or P2 and the bigger surface. So we talked about linear attraction points, principles, and then when we compute, in general now, the extension, if we consider and the distance between the point P and the set S on the direction determined by the point P and the optimal point O, one has the following. We have a negative distance with the point P, and set frontier, if P is inside of the set S, is 0 if P lies on the frontier of the set, and it's positive if P is outside of the frontier. So we see here, we consider again a point of attraction which is inside, not necessarily the symmetric point, may have, for example, a gravitation point, and then the other points falling on this surface. So the attraction lines, supposing they come on a rectangular, on a linear attraction points. So see how the points are attracting from outside towards this one. Now, if it's a point which is outside, P1 is outside, the distance will be positive, and is just the distance between P1 and the frontier of this two-dimensional object, following on a direction between P1 and O, the optimal point. Now, if the point is inside, for example, P3 here, the distance will be negative, and is the negative distance between P3 and the frontier, but again following the attraction line, the attraction direction. And in the same way, if here, if the points are inside, here, if the points are outside, also positive. If a point is inside, it's on a frontier like P4, the distance is 0. Now we have an extension to 3-dimension. So we consider a generalization from 2D to 3D in of the extension set and dependent function. And we assume that we have 2 points, A and B, on 3-dimension, and we draw from A to B parallels to the plane in a Cartesian system X, Y, Z. So we have a photo here. So in a case, we have a 3-dimension distance between a point and a prism. So if a point is outside, for example, this P is outside, and the object is this prism here, we see the prism, and the optimal point is a point inside O, we consider it like the center of symmetry. But if it's not the center of symmetry and any other point, the procedure will be the same, because we connect the point, point P, which is outside, with the optimal point, and then we measure the distance between P and the point where this line intersects the object, so the frontier of the object. So the distance will be P prime, and it's considered positive because P is outside. Now, if we have a point which is inside, let's say alpha, then we measure the distance between alpha and the frontier of the object. So always the distance between the point and the frontier, but from inside, and also following a direction that connects the point to the optimal point, to O. So on this case will be the distance will be A alpha prime, but it's considered negative because the point is inside. We have also the dependent 3D dependent function, which is the distance between any point in a R3 dimension space of coordinates x, y, z, and the object over the distance between the point over the difference of distances between the points and the objects and the frontier. So here we have again the property, if the point belongs to the interior, actually we have the photo down. So the thing is the same like before. The distance between the point and the object, and the difference of distances between the point and the object, and the frontiers. Now, if we consider in general any corp like this one in 3 dimensions, and the attraction point is any point, but the attractions are following linear vectors. So the procedure is the same. I mean, if a point is outside of the object, we get a positive distance. For example, here, P1, which is the distance between P1 and the frontier of the object, but following the line that connects P1 with the optimal point. If the point is inside, or if it's on a front here, it's outside. If it's inside, will be a negative distance like this one, negative distance. And again, outside it's positive, inside it's negative. Now, it's possible also to have nonlinear attraction points. So now we have to compute the distance following the respective curves. For example, if O is the attraction point by the attractions curves are not linear, say like this one, this is not linear, and we want to find what's the distance between P6 and this object in 3 dimensions, we measure the distance on this curve here, because that's how the point is attracted. For example, we may have a point which is attracted in this way because it's not possible to have a direct attraction having many obstacles. So the point has to avoid the obstacles and go on a non-linear curve. Here it's actually formed by 3 lines, small segments of lines. Here, if we have P5, for example, this is attracted linearly, so the distance would be in the same way, the distance between P5 and the frontier, while if we have another point, like let's say this one, P4, the distance between P4 and the object is measured on this curved line. Again, the non-linear attractions may occur because of various obstacles they face, or because the geometry of the object, so the way it is set up. Besides the generalizations from 2D, 3D, and 8D in general, in this book, I also included some applications of okay, 3D generalization I did. Applications of extenics in various fields and also in philosophy. The same thing we discussed before. Let's see applications in more applications. Applications of extenics in 2D and 3D. So we constructed in the same way rectangles, and then we have a factory piece whose desired two dimensions should be 2 centimeters by 30 centimeters, and acceptable two dimensions, 22 centimeters and 34 centimeters. As you see, we work with indeterminacy as in our everyday life, and some pieces may not be produced exactly, but a tolerance is accepted, say 20 by 30, but still we can agree to 22 by 34, so the piece can fit into the general ensemble. So in this way, we have this, the desired one, and then the red one, and the black one means kind of tolerance, how much we can tolerate for the distance, because if we work with very small units, for example, if we work with millimeters, it's very hard to do exactly. Sometimes we have to approximate, and then that was the tolerance we could be doing. Here it's how to compute this one and how to check. So you have the book and you can check it. I don't go into details. And we have the critical zone, which is the zone between the two of them. And here also a case of 3D. If we have a 3D, let's say the red one is the desired one, and the green one, green piece, it's the tolerance. Of course, here it's exaggerated in order to see better the pictures, but they may be microns, working with microns. And then with microns, we have to have very perfect tools to be able to do them exactly. So we work in this way. See, a similar thing if we have for a circular piece to make for a factory needed for some engine, for example, the red one will be the desired one, and the green one, it's the tolerance. So if we have microns, how big we can allow it. We have to allow it a little bigger than a little smaller, because if it's a little smaller, we have to redo again. But if it's a little bigger, we can remove little by little from extra dimension in order to get to the real one. Now, generalizations from 2D to 3D and ND, and then you see the formulas. You have all of them here. I also connected it to Extenics, to the famous Chinese philosophy Yi Yang. Now again, generalizations here. Repeating some of the previous work, but doing more things. Here, extension transformation using in I Ching. So the famous Chinese philosophy, ancient, more than 25 years ago, that you're very aware of and you like it. So I was inspired by this one in constructing the nutrosophic logic. So I Ching is based on the uh, connection, or anyway, the dialectics between positive and negative, between male and female, uh, and in general, as I said, between some object, some idea, or some object, something called H, and anti-H, meaning the opposite. So yin and yang, but also, as I observe, uh, is not only the dialectics between the opposites, but also the neutrals between them, because the neutrals also interfere. Let's say two countries go to war. So the two countries are the opposite, H and anti-H. But many neutral countries uh, react. Some neutral countries help H, others help anti-H. Other neutral countries also remain neutrals. So in European philosophy, inspired by I Ching, although they never said that, they developed the so-called dialectics developed by Marx and Engels, German philosopher, and they consider the same thing, only the dynamics of opposites, H and anti-H. So in neutrosophy, I added neutral H, so the neutral part between H and anti-H, because that happens all the time. Let's say another simple example, two people are fighting. Okay, if they're fighting, then there are neutral people around that try to intervene, either to help one or help the other one, or just separate them, not to fight. So the neutrals have an important contribution to the fights between the opposites. So I call it neutrosophy. Neutral means the neutral part also has a very important uh, thing. Now, when I was in 2012, my pleasure to be in China. I visited China actually 5 times, invited, and I had many presentations, and I cooperated with many Chinese researchers, which are very strong and nice people. So I read many things. I read about uh, Chinese philosophy. about I Ching, the Book of Change. I got books when I was especially in Guangzhou, and then I tried to connect them to Extenics because I work on Extenics at that time, and also at that time I had done already the nutrosophics, and then I connected them with the nutrosophics. Lao Tzu, also I read the philosophy, the art of war, very interesting, very, very interesting. So I learned also about Chinese traditional medicine that I even practice here in the United States because they are very interesting. So now using the hexagram from I Ching, um, I try to connect the hexagram with anti-hexagram, I call them, and then they correspond to 62 neutral hexagrams. So again, going on Yang Yin philosophy and connect them to neutrosophy, and then I made hexagrams. I put them here. See the hexagrams. So the book is it's more complex or has many things. So I cannot go in detail because I have only 30 minutes to present. And then you can see the book. So how to present H and how to present anti-H. And further on, how to present neut H, meaning a combination of H and anti-H, because we have a combination of opposites. Yeah, some person is good from a point of view and maybe bad from another point of view. So everybody has degrees of truth, degrees of falsehood, and also you may say degrees of neutrality or unknown. Here I did a circular hexagrams, also based on I Ching and adding to Yang Yin philosophy, also adding the nutrosophy. So just a few more things about this one. Then some people from Romania were inspired by Extenics and consider Extenics in conventional and non-conventional, and we wrote a paper in Romanian language. So how to do the transformation of space-time using Extenics and considering the universe of entity and also the dialectics between positive, negative, and then the neutral. So the neutral part between them, between irreality and reality. So we try to use this one in order to expand more the extenics. Now the conversions between connection between infinity and zero. So I mean the opposite, to consider the case when 0 times infinity is 1, of course in calculus and using limits. I go a little further because the paper is in Romanian language. I should translate it into English. And then we did extension communication for solving the ontological contradiction between communication and information. So we may have communication or communication of information or misinformation. So how to be able to distinguish between information and misinformation, communication and miscommunication, and using Extenics as well. So I think this is the last paper. I thank you very much. And then here you have about this work. So I was happy I work in Guangzhou with the Chinese Association for Artificial Intelligence and especially Extension Engineering Society. And then I did research. I may be able to come back again to do some more research. So in 2012, I work at the Research Institute of Technology with many researchers. And then I work with Xingsen Li, Professor Kai Wen, Mihail Livius Smarandache. My son came there also, invited by Professor Kai Wen, and did research on and help on website for Extenics. Also Xin Li. So there are many other professors that I work with. We have presentations, photos, and I wrote a small paper about Professor Kai Wen after his passing away. And I thank you very much, and let's keep in touch, and then maybe another time I'll show you a presentation about neutrostrophics. Thank you very much. Ni hao, xie xie. Florentine Smarandache, United States.